Hello, everyone. What I want to talk about now is bounded linear maps. So we're going to start chapter 2. We all, of course, know what a linear map is. Let's say I have two vector spaces. Of course, in this course, we always need uh, well, for this course, really, we're basically just going to deal with a normed vector space. Um, in general, in functional analysis, you always need some kind of topology here. Um, so let's say we have two normed vector spaces. Okay, so we say this is linear if, well, the obvious thing is true. For any scalars, alpha and beta, and any elements x, let's say x1 and x2 in big X. This is going to be alpha t x1 plus beta t x2. Okay, right. And often we'll say t is a linear operator if it's a linear map. So we have the following proposition, and we've basically proved it in one of the videos on bounded linear functionals, so I'm definitely not going to prove this. So for a linear operator t, linear operators t, from x to y, and yeah, it's basically the same thing from the video on bounded linear functionals. T is continuous. And of course, the complex plane or the real line is a normed vector space. So bounded linear functionals on a real or complex vector space, complex normed vector space, real or complex normed vector space, sorry. That's a special case of y being the real line or complex plane. Right, so t is continuous on all of big X. T is continuous at little x equals 0, thanks to linearity. And 3, what we colloquially call the operator norm is bounded, which is just the supremum of Tx over all x with norm less than or equal to 1. So it's a real pain to kind of denote what norm vector space the norm we're dealing with is. So we'll often not bother if we don't have to. If I really omitted y here, well, t takes x, spits out something in big Y, so it's pretty clear that the norm here is y, and x is in big X. Big X is a norm vector space, so it's clear the norm here is x. So, all right, and yeah, like I said, proof practically already done. So, an important note, actually two notes. Let's say we have an x that's not equal to 0. So tx, well, again, only norm that makes sense is the y norm here, because if little x is in big X, t takes in little x and spits out something in y. So implicit is that this norm is y. Okay, so this is going to be equal to the norm of x. So kind of multiply and divide by the norm of x and use linearity. Well, certainly what I have here circled has norm less than or equal to 1. The norm of this is obviously equal to 1. So this is less than or equal to x times this operator norm. And usually this is written by, it's the norm of t. And again, unless otherwise specified, this is really the only norm that makes sense. Or at least this is, if I don't specify a norm for an operator, then it's going to be this norm here. Okay, so this is definitely something you want to remember, and this is assuming one of these are true, which imply, they're all equivalent to 3. And I should mention, this is finite, of course. I meant that this here, the operator norm, is finite. Okay, so assuming the operator norm is finite, and I should say, we say a linear operator t is bounded if any of these, equivalently all of these, are true. So if t is a bounded linear operator, then we have this very useful inequality here, that the norm of tx is less than or equal to the norm of t times the norm of x. All right, so let me prove at least a good chunk of the following very useful theorem. So from now on, let's say b of x, y for two norm vector spaces x and y. Let's say this is going to be all bounded linear maps, bounded linear operators, same thing, from x to y. So again, by definition, that means that one of these are true, which implies all of these. Okay. So the theorem is, well, x is a normed vector space, y is a normed vector space. If y is a Banach space, then this is complete. This is a Banach space. Under this operator norm. So a lot of times you'll see the norm denoted by a b of x, y here. It's a little easier to write this here. So. Okay, so from linear algebra that linear maps from one vector space to another form a vector space. So I'm not going to prove that. That's pretty trivial. And proving that this is actually a norm, I'll leave for you. Probably won't collect it. That's also not much to that. In particular, obviously, this says if the operator norm of t is 0, then tx is just the 0 map. Tx is just 0, because you have 0 times x. And of course, when x equals 0, this is just 0. So yeah, the operator norm is 0. Sorry about that. Didn't mean to put up the calendar. Right, so yeah, basically it's very easy to show that this is a norm. All right, so let's prove completeness, or at least prove kind of half of completeness. I'll leave the other half for a homework, since we've kind of done proofs similar um, in lecture and in homework. Okay, so let's say we have a Cauchy sequence. Cauchy with respect to this operator norm. So this is not a hard result to prove, because this is a very strong statement. This is very powerful if the supremum is finite. So let's assume this is Cauchy. So if x is not equal to 0, then let's look at the following here. So yeah, anyway, I'll talk more about the consequence of this in a second. Okay, so what I want to do is, I want to prove that Tn applied to x is Cauchy. If that's true, then because y is complete, Tn of x as n goes to infinity will converge to something. And I'm going to define my linear map from x to y to be that something. So in particular, let's show that this is Cauchy. So by the definition of the vector space structure on bounded linear maps from x to y, this is just Tn minus Tm applied to x. It's really the definition. This is a bounded linear map. So this is going to be less than or equal to the operator norm Tn minus Tm times the norm of x. Okay, so let's say epsilon is positive. Pick n, a natural number n, such that, well, just restate what it means to be Cauchy. And m bigger than n implies Tn minus Tm. What I want is this to be less than epsilon over the norm of x. So let's be a little careful here. I guess I'll use red. So this absolutely depends on epsilon. Well, obviously it depends on epsilon, but also depends on x. Certainly as x is non-zero, but is, if x gets larger and larger and larger, we need perhaps n to be itself larger and larger and larger to get this is true. Because epsilon over x for x larger and larger, larger is smaller and smaller and smaller. Okay, right. So the punchline here is nm bigger than n implies Tnx minus Tmx, should use capital. That's going to be less than, well, epsilon norm of x, epsilon over norm of x times norm of x is going to be epsilon. This is true for any epsilon. So that means that this is Cauchy as a sequence of stuff in Y. Okay, so we know it exists, this limit, so let's denote the limit as y, whatever it is. All right, so let's define a map from x to y, big X to big Y, big X to big Y by Tx is this element y, whatever it is, this limit here. Okay. Just take a step back, and this is certainly a nice, well-defined, no issues map from big X to big Y. Given something in big X, let's call it little x, Tnx is Cauchy, it converges to something. Let's say that something is Tx. It takes in something in big X, spits out something in Y. Okay, so no ambiguity whatsoever. Okay, right, so linearity is easy. Really, yeah, there's really not much to that. I'll leave that for an easy exercise. I probably won't collect it. Yeah, linearity, just because right, because Tn is itself linear. It's really not much to that. Maybe I'll just run through it. T alpha x1 plus beta x2 is by definition this limit here. Obviously, yeah, Tn is linear, so you can pull out this constant. And that's just going to be T alpha Tx1 beta Tx2. Okay, so to finish up will be for homework. So in particular, homework will be that T is itself actually a bounded linear map, or sorry, it's bounded. We proved it's linear. And I'll let you prove that this equals 0. So in particular, Tn does converge to T. Okay. Second. Sorry about that. Had a sheet of paper fall to the ground, which was my next piece of lecture notes. Okay, right. So an important corollary is following. So yeah, so let's say X is a normed vector space. So I know I had star for the completion. That was probably not probably regrettable notation. Don't know, didn't really know what else to call it. Usually X star denotes the dual space. And the dual space is as follows: the set of all linear maps from X to Well, either C or R, depending whether X is a vector space over the complex numbers or the real numbers. So this is by definition what the dual space is. Okay. So in particular, both C and both R are complete, obviously. So no matter whether X is complete or not, the dual space is always complete, which is very useful. Okay, so let me basically finish off this lecture with some interesting examples, because there's plenty of them. The first example you might or maybe not have seen, and that's just multiplication operators. In the next video, we will talk about adjoints of linear maps, and yeah, I mentioned maybe I'll do actually the Lax-Milgram theorem, because it's a pretty easy consequence of existence of adjoints, basically. Anyway, we'll see. And it is very important. I use it all the time in my research, Lax-Milgram. Okay, so let's say X is LP of the real line, or Rn, doesn't matter, for P between 1 and infinity. Okay, let's say F is in L infinity. And define multiplication by F. Well, just F times G, nothing too fancy here. Certainly, it's pretty trivially in LP. So I claim that the operator norm from LP to LP is equal to the L infinity norm of F. So you rarely can compute operator norms. It's fairly special when you can, but here you can. Right. Right, and I think this actually might have been a prelim problem in past days. Anyway. Okay, so let's assume F is not equal to 0 almost everywhere. So if F equals 0 almost everywhere, then, well, F times G is 0 almost everywhere. So this is literally just a 0 operator, just takes everything and spits out 0. So not very interesting. The L infinity norm of 0 is 0, so this is trivially true if F is 0 almost everywhere. All right, so let's say G has LP norm less than or equal to 1. Let's just look at this here, kind of do something fairly trivial. All right, so this is going to be following integral. Obviously, I can pull out the L infinity norm of F, and I'll get this here. So it's this times, well, all you're left with is the LP norm of G, which is less than or equal to 1. So this is less than or equal to the L infinity norm of F. So by definition, this is exactly what MFG is. So by definition, this is less than or equal to 1. What I want, not less than or equal to 1, less than or equal to the L infinity norm of F. What I want to now show is that for any epsilon bigger than 0, we basically have the reverse that the L infinity norm of f minus epsilon is less than or equal to this operator. If we can get that, then obviously, well, this is less than or equal to the L infinity norm of f, so obviously that'll finish the proof that we'll have equality. Okay, so the way you usually do this, pretty much always, is you really just have to cook up. So if you ever want to prove equality for an operator norm, for a very concrete operator, you really just have to cook up a special G to kind of test your operator with and to just extrapolate information from that very special G, or that very special element you're applying your operator to. All right, so so how do I prove this? Well, I'll just remind you of what the L infinity norm is. It's essentially the smallest positive C where f of x is less than C, less than or equal to rather, almost everywhere. And we're assuming this is positive. Right? Well, the smallest might not exist, so the next best thing is the nth. So it's morally speaking, the smallest C where f of x is less than or equal to C almost everywhere. Okay. So let's say epsilon is positive. Oh, we already said that here, sorry. So, so what this means is there exists a measurable subset of R with positive M is Lebesgue measure on the real line, positive measure where f of x is bigger than the L infinity norm of f minus epsilon on A. So in other words, for any, or maybe it'd be a little more clear, this is true for any x in R. And why is this true? Well, the inf is a lower bound of my set. Right, so that means this number here cannot be in this set here. Okay, this is not in this set here. If it was, then the L infinity norm of f would be less than or equal to this number, which would mean 0 is less than or equal to minus epsilon for positive epsilon. That's absurd. So this is not in this set. Sorry about that. So that means f of x is not less than or equal to the norm of f of x, the L infinity norm of f of x minus epsilon almost everywhere. So there exists a set of positive measure where this is true. And this is enough to cook up a very useful G to dump into my operator. Right. So let's say G is a characteristic function of A over the measure of A to the 1 over P. So let's see. Well, first of all, yeah, you can pretty trivially compute the LP norm of G. So this is just going to be, well, it's a characteristic function, so we're integrating over A, and it's 1 on A. So it's going to be 1 over, we'll raise this to the p. Well, obviously that's just 1. So it certainly is less than or equal to 1 in LP norm. It's equal to 1. And let's figure out what this is. Okay. Well, again, it's basically the same thing as this, except insert, well, maybe I'll just do it like this. Right, so it's the same thing as this, except stick in an F. So this is going to be equal to taking this f of x to the p in modulus over the measure of a, 1 over p. But on a, f of x is bigger than this here. So this is bigger, well, bigger equal to doesn't really matter. Sure, make it bigger. So this is bigger than integrate over a, L infinity norm minus epsilon to the p over m of a. To the 1 over p. Had a little brain fart there, sorry about that. Well, you could just pull this constant out. This is obviously a constant right here. I'm circling, so no doubt about that. Pull that out. The p undoes the 1 over p here. Whoops, sorry about that. Well, if you pull this out, inside the integral is just the integral of 1 over the measure of a dx. Well, that's a constant, so it's just the measure of a over the measure of a. It's 1. So it's this. It's equal to this times 1. So it's literally just equal to this. Okay. And I probably should put up here, of course, that because G has norm 1, well, by definition, this here is the sup over all of these LP norms for all G with norm less than or equal to 1. So the sup is bigger or equal to, as an upper bound, any individual one of these with norm G less than or equal to 1. So that exactly proves it. We've carefully proved that the operator norm of this multiplication operator is bigger than the L infinity norm of f minus epsilon for any epsilon. So we actually proved, I mean, it's equivalent, obviously, for any epsilon, but we actually proved this just now. And that completes the proof because of, again, this one right here. Okay. Yeah, so in general, and it's for a lot of concrete operators, it's often, a fruitful research endeavor. In particularly special cases, trying to figure out what the operator norm of something is. Okay, so let me give you a few more examples. This example here is going to be an easy homework. Let's say I have a Hilbert space H, and M is a closed subspace of my Hilbert space H. And let's say I have the orthogonal projection from H to M. homework is that you actually have that the norm is going to be equal to 1, no matter what it is, as long as this is the orthogonal projection. And this is from H to M. So yeah, these are quite special. So in particular, this is a bounded linear map. Okay, last but not least, before I talk about something I've done a lot of research on, more so in the past than recently, which is Toeplitz operators, I want to first prove a very easy proposition. I don't need to write important, but it is very important. And it's really so easy, I don't think it's worthwhile to call it a theorem. It's the following. Composition is very nice. If I have A, bounded linear map from X to Y, say X, Y, and Z are all normed vector spaces. Let's say I have B, a bounded linear map from Y to Z. Then a B, do BA, not that it matters much, but BA is going to take, well, take an X, A spits out Y, B takes in Y, spits out something in Z. So this is bounded from X to Z. And in fact, the operator norm from X to Z is less than or equal to the operator norm of B, operator norm of A. Right. And I would give this for homework, but fortunately, the book provides plenty of homework, so I don't want to do too much for homework. And the proof is very straightforward. Let's just say X has norm less than or equal to 1. So we need to look at this composition here, BA applied to X. The operator norm is the sup of all of these. Okay, so by definition, this is, well, obviously just B applied to AX. But AX is itself in Y. So this is less than or equal to the norm of B times the norm of AX. But the norm of AX is itself less than or equal to the norm of A, operator norm of A, times the norm of X, which we're assuming is less than or equal to 1. So take the sup over all X and norm less than or equal to 1. Or because X was arbitrary, this means that the operator norm of BA is less than or equal to operator norm of B, operator norm of A. And that's really all there is to it. That BA is a bounded map from X to Z. It's just from the linearity of A and B. Okay, so yeah, let's talk about Toeplitz operators. And the book talks a little bit about this too. The book actually has homework in Toeplitz operators. Okay, so let's say I have something bounded on the unit disk. I can use this, this bounded function, bounded measurable function on the unit disk to define a map called the Toeplitz operator, named after Otto Toeplitz, who studied this on the Hardy space. That's very beautiful properties that make it extremely useful in applied math. I don't know if I'll talk about even the Hardy space in this course. Maybe I will. Plenty of things to do for the Bergman space. So, but anyway, yeah, basically same definition on the Hardy space as it is for the Bergman space. And for the Bergman space, this is going to be for F in my Bergman space. This is going to be the projection times multiplication by phi times F. So you can write this as a concrete integral operator. And it's often very fruitful to not so much think about it as a Hilbert space projection composed with multiplication, but just to think about it as an integral operator, because the orthogonal projection is an integral operator. So right, so I'll write down what's going on in a second, draw a little diagram. Right, so this is an integral operator with kernel, this function here over 1 minus ZW bar squared. Okay. Right, so I should mention that 1 second. Right, so just if there's any confusion here, obviously, if F is an A2, that implies, basically, we showed this already, that the L2 norm of, basically just pull out the L infinity norm of phi here. I'm sick of writing the disk, so I won't do that. So certainly if phi could be pretty nasty. It might not even be pointwise defined. So there's no reason why this is an L, there's no reason why phi F is holomorphic, but at the very least it's an L2. And what's the point there? The point there is, at the very least, then you can apply the orthogonal projection to get something that's back to the Bergman space. Okay, so the idea here is you apply multiplication to go from A2 to L2. Could very well disturb holomorphic, the holomorphic, or F being holomorphic. Well, you want to kind of go back to the Bergman space. Via the orthogonal projection, you compose these two, you get this Toeplitz operator. Okay, so that's the idea. Okay. So something interesting to note, if actually this is holomorphic and bounded, well, yeah, so let me, so if it's holomorphic and bounded, then, well, this actually is holomorphic and it's an L2, so this is an A2. So what does this mean? This means this Toeplitz operator is not that interesting. The orthogonal projection is just the identity on A2. So this is just really multiplication by phi, which is still kind of interesting. Okay. In general, I want to look at the operator norm of my Toeplitz operator. And we're going to just get an estimate for this, a very trivial estimate. Just from the little proposition we had before. So this is less than or equal to, well, the operator norm of this orthogonal projection times the operator norm of this multiplication. And by exactly the same argument we had before, this is literally going to be equal to, well, this is equal to 1. This is equal to the L infinity norm of phi. So this is certainly bounded. I mean, yeah, it's bounded because it's the composition of two bounded linear maps. And we have the following inequality. In general, it's notoriously challenging to find the operator norm of a Toeplitz operator. You often want to do it in terms of, more sophisticated measures of the size of your function here than just the L infinity norm. And treating this as an integral operator, forget about projections, anything, just simply kind of saying, well, okay, let's ignore this definition here and just kind of skip over to here, just defining this Toeplitz operator as an integral operator. Most certainly you can get unbounded functions phi giving you bounded Toeplitz operators. But I don't really want to get into that. It's getting us way too far from this course. So one thing that I will have you do, well, I guess you don't really have to do it if you don't want to, but if you want the points on the homework that I'm going to assign, as actually, I think this is might even be one of the earlier problems in the book in this section. Maybe it's even problem 2. Well, actually, I'm going to generalize the book's homework a little bit. So in a very, very special case of a Toeplitz operator, you're going to compute the operator norm of this Toeplitz operator. Here, this function is not that amazingly special. And we still have to do some work. It's not trivial at all. But for any natural number m, if phi is z to the m, then this operator norm is going to be equal to 1. And the hint will be test this Toeplitz operator on your canonical orthonormal basis elements that we talked about maybe 2 or 3 videos ago. So this will be part of a new homework that I'll collect and I'll assign maybe in like a week or 2. But all right, yeah. So next time we'll talk about Hilbert space adjoints, and basically maybe another video or 2 finish up the basics of bounded linear maps and bounded linear operators. And what's the 3rd chapter? I think what's called the big 3, which is really the I would say Hilbert spaces. Well, Hilbert spaces, bounded linear operators, and the big 3 are kind of like the meat and potatoes of the course. Hahn-Banach, principle of uniform boundedness, and closed graph theorem. All right, well, hopefully this was interesting, and yeah, I'll try and average 2 videos a week. I think that's pretty fair. Roughly 2 hours of videos every week. But as always, if you want me to go faster, I don't know if it's even possible to go slower, but if you want me to go faster, I'll be happy to go faster. All right, so long. Take care. Bye bye.